Okay guys, hopefully you've printed off the sheets already for today. We've got one more topic to go through. We're going to split that topic into two parts. Today we're going to practice the calculation involved in this work, and then next day we're going to practice how to apply it to actual diagrams of circuits. It looks like diagrams are going to be important today. Because of the front of this page, they're not. Today we're just going to learn the calculations. So the work that you have to do is called equivalent resistance. And what this means is when you have more than one resistor or more than one lamp or more than one load in a circuit, there has to be a way that you can calculate what the total resistance is for the circuit itself. But we don't like to use the word total. This could be called total resistance. It's not common practice to use the word total because total always implies that you add them together. And although you do always add resistors together, there is a difference with parallel circuits. When you add them together, you get a number that's lower than what you see in the diagram. That sounds a little confusing, but let's go through this step by step and you'll see what I'm talking about. So first of all, for a series circuit, the formula for equivalent resistance for a series circuit, and I probably could have had you read this out of the textbook. It would have been faster than following along in this video, but that's okay. The formula for equivalent resistance in a series circuit is taking resistor number 1, adding it to resistor number 2, dot, 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 and just keep on doing that same pattern. So basically, it's a really, really easy formula. And a tragedy that you didn't get to this in grade 9 if your teacher was worried about the mathematical component of grade 9 science. All you do is add them up. But it is grade 11, it is the university level, and although you can glance at this diagram and just say, oh, the answer is 60, I can see it, 30, 20, 10. It's still university level grade 11 work. You still have to do this. You would still have to say, okay, my equivalent resistance is R1 plus R2 plus R3. I'd have to fill in my substitution line that I've got a 10 ohm resistor and a 20 ohm resistor and a 30 ohm resistor. And then finally I could put down the answer of 60 ohms. Sounds like a tedious little bit of work, but remember, that's what you're going into. You're a university level student, and you're leaving high school and going to university where they're going to expect full format to the work all the time. So series circuits are really easy. You literally just add the resistors together. Parallel circuits, a little tiny bit different. You still add the resistors together. However, the formula is you add the inverses of the resistors together. So it's very, very important that on the left-hand side of the formula, you write down 1 over equivalent resistance equals 1 over R1 plus 1 over R2 plus dot, dot, dot. Doesn't matter how many you have, you could have 50 resistors. This is the formula. And although it feels like you could just glance at this diagram and say, oh, the answer is going to be 1 divided by 60. That's not the case. It doesn't work out that way. So what you have to remember with parallel circuits is don't ever try and do any kind of a shortcut. Do it fully mathematically and see what the answer is going to be. Don't ever try and guess because you won't get it right. So for this parallel circuit, there are 3 resistors, 10, 20, and 30. The only way I can get the correct answer is I have to add the inverses of these resistors, and I have to remember the left-hand side of this formula is inverse. So I have to add 1 over R1 plus 1 over R2 plus 1 over R3. Substitution line. 1 over 10 ohms plus 1 over 20 ohms plus 1 over 30 ohms. Do not add those 3 together and say it's 1 over 60 ohms. That is absolutely mathematically incorrect. You did this kind of stuff in grade 9, but they taught you to find a common denominator. So you'd have to pick up a common denominator for this, 10, 20, and 30. A common denominator is 60. and you'd have to modify each one of those fractions before you can add them together. Da-da-da-da-da-da. Forget it. It's grade 9. It's not, or sorry, it's grade 11. It's not grade 9 math anymore. Convert these to decimals right away. Don't waste your time with common denominators. Seriously, take out a calculator and do each one of these if you need to. Have another line of work. Convert these into decimals. 1 divided by 10 is 0.1 ohms. 1 divided by 20 on a calculator? Seriously. Don't try and do it in your head. Do it on a calculator. 1 divided by 20. 0.05. 0.05 ohms. 1 divided by 30, I have no idea. What do we got? Oh, it's a repeating decimal, but so what? 0.033 repeating ohms. Now you do not have to find a common denominator. Now you can just add all three of these together and have an easy answer where you don't have to go flipping fractions around. Okay, so final answer comes out to 0.1833 repeating ohms. That's mathematically correct for what I have written on the page. That's not the right answer. And I did it on purpose because I wanted to point this out. This is what you always, always, always have to remember about parallel circuits. The left-hand side of the formula, right here. It's not REQ. It's 1 over REQ. So what you have to remember, and it's kind of like the work you did in grade 10 optics when you had focal lengths and distances, because that was a fraction formula as well. When you get to the final answer on the right hand side, you're not done yet. This is 1 divided by REQ. That's what it equals. You still need to isolate for REQ. Easiest way to isolate is, well, there's different ways to think about it. I could flip this fraction and flip the right hand side. Let me do it this way. If I bring REQ over to the right, it's a denominator on the left hand side. Bring it to this side, it'll be a numerator. And if I bring the 0.1833 to the left hand side, it will go underneath. And I want to remember to repeat all those 3's. Okay, so there's the answer. It's going to be 1 divided by what I thought was the answer before. That gives you a final answer in the end of 5.45. And it repeats. That's the true equivalent resistance for this parallel circuit. So you can see, this is why we don't like to talk and say total resistance, because if you're looking at a parallel circuit, you're going to think, oh, the total is 10, 20, 30. It's somewhere around 60. The total of those 3 resistances is actually only 5.5, which is kind of weird. But that's the way parallel circuits work, and that's why you really just have to follow the formula. And don't ever try and guess. Okay, we're not going to do any examples today because really, this work is so easy, the examples would match the questions. So what I would rather have you do is answer these 4 questions. The first 2 are actually exactly like what I just did on the first page, come to think of it. And then the last 2 have a slight variation that makes them something just slightly more than subbing into the formula. You'll definitely get the answers for the first 2. The answers are actually written on the page for the first 2 anyway, so confirm that you know what you're doing by doing 1 and 2. Get the answers. And then try 3 and 4, and I didn't put answers on the page for 3 and 4, so you'll have to wait for these ones. We'll take these up. I'll post some written solutions to these questions. And once you understand how to do these 4 answers, we'll move on to the very, very last thing of the year, where we're going to take this work and apply it to some circuit diagrams.